All right, let's jump straight into this explainer and crack the exact Cambridge framework you need to absolutely ace your 0625 physics exam. Today, we're mastering background radiation and locking down that high-mark exam strategy. So, we are kicking things off by putting a painfully common student mistake right on trial. When faced with a question asking to explain background radiation, so many students just panic. They write down the very first thing that pops into their head without actually filtering it through the Cambridge marking criteria. Let's take a look at the main suspect.
Okay, reading this, background radiation is just the dangerous radiation around us caused by nuclear power plants. Honestly, writing this on your paper puts your grade boundary at severe risk. Now, it kind of sounds vaguely correct to the untrained ear, right? I mean, it mentions radiation, it blames nuclear power plants, but in the ruthless eyes of a Cambridge examiner, this testimony is fundamentally flawed and literally misses the core physics entirely. By the end of this explainer, you'll know exactly why.
The real problem with answers like the one we just looked at is that they rely on casual, everyday assumptions rather than strict, scientific precision. Think of it like a house of cards. If you lose marks on these easy foundational definitions, your whole foundation just crumbles when the exam scales up to those nasty data analysis or half-life calculation questions. We simply cannot afford to leave these easy marks on the table.
So here is your first quick win. This is the definitive, examiner-approved textbook definition. Background radiation is the continual exposure to radiation from a range of radioactive sources, both natural and artificial. Notice that specific wording. It's not just a one-off event, it's a continual exposure. And to actually secure those marks, you absolutely must explicitly state that these sources are a combination of both natural and artificial. That phrasing, totally non-negotiable.
To really wrap our heads around this concept, we need to take a quick trip back to 1896. French scientist Henri Becquerel actually discovered radioactivity completely by accident. And that was followed really closely by Marie Curie's groundbreaking discovery of the element radium. They basically realized that unstable nuclei were emitting something completely invisible to the naked eye. It's a phenomenon we now know happens naturally all around us, and of course can be triggered artificially in reactors.
And Becquerel's experiments brilliantly illustrated his key findings. He found that the radiation from uranium compounds completely penetrated solid black paper to affect a photographic plate. And, crucially, it had an ionizing effect on a gas. You really want to remember these two specific properties: penetration and ionization. Why? Because they are exactly how we detect and measure background radiation to this very day.
Now, in just a second, I'm going to show you the precise examiner clue that completely transforms your exam answers. But first, you need the underlying framework that actually makes that clue obvious. Stick with me here, because missing this next framework essentially means kissing full marks goodbye. Memorize this categorization coming up, and I promise you will never drop points on a radiation source question again.
Section 1. Identifying radiation sources.
Right, so the crucial point for the examiner is your ability to split these sources right down the middle into two distinct camps. On the natural side, we've got cosmic rays, radon gas, and potassium-40. Then, over on the artificial side, you have medical procedures, nuclear power stations, and nuclear bomb fallout. Let's actually investigate the natural sources first, because examiners absolutely love testing you on these specific mechanisms.
Pay really close attention to the specific details here. Take radon gas, for example. It's emitted from granite rocks and can dangerously collect in poorly ventilated basements. This is a super common exam scenario, especially popping up in questions about homes in Scotland where granite is everywhere. Then you have cosmic rays, which are just high-energy particles raining down from the sun. Oh, and here's a fun little fact for your exam. Radioactive potassium-40 is naturally absorbed by our bodies through the food we eat. That basically makes bananas slightly radioactive. Now, obviously, you'd have to eat millions of them at once for it to do any harm, but it perfectly proves the point that we are constantly surrounded by natural radiation.
Now, flipping over to the artificial side, you must be able to specify that nuclear fallout produces strontium isotopes. These bad boys have incredibly long half-lives, which means it takes decades for their radioactivity to decrease by half. And because strontium behaves chemically a lot like calcium, it gets absorbed directly into human bone. That's what makes its long half-life so exceptionally dangerous. Honestly, this is a brilliant high-level example to drop into your exam. It perfectly ties real-world applications directly to severe biological impacts.
Okay, so the syllabus demands you know how to detect all this invisible stuff. So how do we practically, physically prove that this radiation has an ionizing effect? We know from our buddy Becquerel that radiation ionizes gases. But how would you actually demonstrate this in a school laboratory? Or, more importantly, how would you describe it for a practical exam question?
Well, here is exactly how you build the perfect practical answer. Step 1, you charge an electroscope. Step 2, you bring a lighted match or a radium source near the cap. Now wait, for those crucial exam safety marks, you must explicitly state that the radioactive source is held using forceps. That maximizes the distance from your body. Finally, step 3, you observe the electroscope discharge. What's happening is the radiation ionizes the air around the cap, neutralizing the charge, which literally causes the gold leaf inside to physically fall. It's a classic, highly testable experiment.
Section 2. Acing the exam question.
So it's time to head back to our courtroom and build an absolutely airtight case for the examiner. If you want top marks, every single answer you write must cycle through this 4-step elite framework. First, state the core physics concept. Second, back it up with evidence or data from the scenario. Third, apply scientific reasoning to link them together. And fourth, lock the whole thing in with precise examiner wording.
The verdict is officially in. Let's compare our initial suspect to the top band answer. Remember that flawed answer? It was vague, non-scientific, saying radiation is just around us from nuclear plants. But look at the elite answer. It explicitly hits the concept of continual exposure, it provides rock-solid evidence by listing both natural sources like cosmic rays and artificial ones like medical radioisotopes, and it uses the precise vocabulary you need to confidently walk away with full marks.
All right, let's do a quick pause and predict challenge to test your instincts. What are the 2 fatal scientific errors in this statement? Cosmic rays come from the Earth's core and cause a charged electroscope to gain charge. Read that one more time carefully. Do you spot the mistakes?
An examiner would ruthlessly cross that out with a giant red pen. First off, cosmic rays originate from the sun and deep space, definitely not the Earth's core. Secondly, the ionization of the air neutralizes the charge on the electroscope, which causes it to discharge. It absolutely does not gain charge. Trust me, catching these tiny details is exactly what separates the good students from the absolute top-tier ones.
You know, mastering the theory is really just step 1, but practicing these specific examiner frameworks is how you actually elevate your overall performance. To make sure you never miss out on these critical strategies, go ahead and subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE. We're here to help you totally excel in your Cambridge exams.
So you've got the theory locked down now. But what happens when you're sitting in the exam hall and you misinterpret the background radiation count rate data in your practical exam? Calculating a corrected count rate by subtracting background radiation is where the real mathematical challenge begins. And sadly, it's where a lot of students trip up. Are you ready to dodge those data analysis traps? Well, that is exactly the problem we are going to solve in our next Essential Explainer. I'll see you there.